So I'm sorry that in today's lecture things didn't go entirely as I planned. Concerning the practice of textbook problems, we actually did all the types of problems, but I would have liked to do more from each type, which we shall do in this video. The reason this happened is because I had to spend a larger portion of time in explaining the theory, something I believe I had to do. Uh, I mean, so like just doing the textbook problems uh, without having a simple idea, like a basic idea of how things are going, uh, what's going on in the background. I don't think that's a good idea. That's a good thing to do. But of course, I had problems in downloading your responses regarding the question, uh, like how many hours you exercise per week. So that also muddied up my theory portion a bit. So here it goes. Since I do not have such time constraints for a video, I'll go into details and I'll start with the theory. So we have learned about random variables. So there is some experiment, and for that experiment you observe or you measure or you count something, and that becomes the random variable. For example, the height of a randomly chosen UW student, or the number of siblings you have, or the annual salary of a randomly chosen Florida citizen. Now, we know that random variables can be of two types, discrete or continuous. So we have done all these things before. So what's discrete? A discrete random variable x takes specific values x1 through xn with probabilities p1 through pn. That means probability x equals x1 is p1, probability x equals x2 is p2, dot dot dot, probability x equals xn is pn. And all this can be given out in a table format, as is given out here. Also from this table, we can know the mean mu from this formula, which we did in exam 1, and we know the sigma given by this formula, also done in exam 1. So in exam 1, you actually solve these questions. So for example, x is the number of siblings you have. The distribution of siblings is like you can have 0 siblings, 1 sibling, 2 siblings, 3 siblings, 4 or 5, with probability 0.2, 0.3, 0.2, 0.1, 0.1. So if someone asks you what's probability x equals 4, you can simply say probability x equals 4 is 0.1. That's it. Like nothing else is going on. Similarly, x can be also continuous. So what's a continuous random variable? So literally, let's go with the lines. So it's continuous if x can take all values in a given range. So the word given range is important, and x can take all values. So for discrete, it takes only this value or this value or this value, like that. But x can take all values in some range. So for example, height of a randomly chosen UW student. So what's the range here? I mean, I'm measuring the height in feet. So the range is like from 4 feet to 7 feet. So from 4 to 7. And in that range, can x take any value? Yeah. Pick out any height between 4 to 7. Is it possible that x equals that number? Yeah, it's possible. So for continuous, we have PDF. Once again, we have done this. So what's a PDF? So suppose someone tells the question, like someone tells you like x has PDF blah 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 dot dot dot. What does that mean? Someone tells you x has this PDF, this picture drawn here. What does that mean? It means three things. First of all, this graph that I have drawn over here should always remain positive or zero. Like it cannot go below zero. Like PDF cannot take any negative values. Next, total area under the curve is 1. That sounds like some math thing, but all it's saying is, so this shaded area on the left, that's a total area under this curve, and that's like 1. Why is it 1? Because total probability is always 1. And the third is the one which is most useful to us. So suppose you want to know the probability that x lies between two numbers a and b. Any two numbers a and b, probability x lies between those two. Then your answer is this much shaded area. So on the right, I've shaded the area between a to b, and that's actually the probability. So that is the job of PDF. PDF satisfies these three properties, and it helps us. Now remember, for discrete, we did mu equals this formula, sigma equals this formula. But for continuous, there is also mean mu and sigma. But what's mu and what's sigma? The thing is, it's not needed. See, mu is some complicated formula and sigma is some other complicated formula. What are those formulas? We don't need it. So mu and sigma will be given to you for the exam and for your homework. Once again, it's not that there is no formula. So for each graph like this, there is a formula, but the formula you don't need. So I'll simply tell you something like mu equals 5, sigma equals 7. How I got the number 5, how I got the number 7, you don't need to worry. One obvious point, someone asks you what's probability x less than c, you just shade all the area left of c. You want to find probability x bigger than c, you shade all the area to the right of c. And I guess you know that. So that's it, like discrete and continuous. Next, you will hear the word population distribution of x. Sometimes we also call it just distribution of x. What does that mean? That means you have taken a sample, and suppose you are measuring heights. So x is the height. So you have taken a sample, and there's like a randomly chosen person. X is the height of that person. Or suppose you're having number of siblings, like you're measuring that. So choose a person at random. X is the number of siblings that randomly chosen person have. So obviously x is a random variable. You have chosen a person at random, and x is something about him. So something about a randomly chosen person is random. Like the height of a randomly chosen person is random. That's obvious. So x is a random variable. Now, x can be discrete or x can be continuous. We have covered this. Like in the sibling example, x is discrete and it has like the following table. Or in the height example, x is continuous and it has some PDF. So discrete things have tables like this, and continuous things have PDFs like this. So what's population distribution of x? It's either the table, if it's like discrete, or it's the PDF. So once again, population distribution of x is the table when it's discrete, or it's the PDF when it's continuous. Now we come to our topic for 6.5, central limit theorem. In short, it's called CLT. The things that we don't need to know for CLT. So I don't need to know whether x is discrete and has this table, or I don't need to know whether x is continuous and has this PDF. So the distribution of x, this table or this PDF, I generally don't need to know. There's a small exception to that, but generally I don't need to know whether it's like there's a table, where is the table, what are the values, so what small x1, what small x2, what small p1, small p2, small pn, small xn. I don't need to know. Or suppose it's like a continuous, then I don't know how this graph should look like. I don't need to know any of this. The things I need to know are like the mean mu and standard deviation sigma. So remember, for discrete, we have a mean mu like this and sigma like this. So I don't need to know this table, but I need to know this mu and this sigma. Also for continuous, we know that mean mu is some formula which we haven't learned. Sigma is some formula which we haven't learned. But I don't need to know this diagram. This graph I don't need. What I need is the mu and the sigma. If someone gives me that, I'm happy. So I need to know mu, I need to know sigma. And the assumptions need to be satisfied. So what are the assumptions now? There are two assumptions. Number one, n is bigger than or equal to 30. And number two, population is normal or close to normal. Okay, let's see. So this number one and number two should be like either or. This or this. So, okay. I'm sorry for that. Just a second. So it's a either or. So either 1 is satisfied or 2 is satisfied. I don't need both. One of them would be good enough. So n bigger than or equal to 30. By the way, what's n? N is sample size. So I need a large enough sample. And by large I mean bigger than or equal to 30. Some of you may think that so 30 does not seem that large. You are correct. For particular applications, 30 is actually a very small sample size. But for our math purpose, this will do. So either n is bigger than or equal to 30, or population is normal or close to normal. Okay, so by population is normal, I mean, that means I know that x is continuous. So I know that x has a PDF, and the PDF is like x is continuous as a PDF, obviously. But the PDF has to be something like this, like normal. This is how a normal PDF looks, like normal or very close to normal. Something like this is not good. Like the one on the left, the PDF on the left is not good. So you may think, okay, why is he talking only about continuous? What about discrete? So no. So assumption number 2 is, first of all, x is continuous and it is a PDF which looks like the correct kind of PDF. It looks normal. So the population is normal. That means first of all, the population has to be continuous. Like the random variable x has to be continuous. And x has to be like normal or very close to normal. Something like this will not do. So now you may be thinking, how do I know that? Like sample size I can see. Like if you give me like 35 data points, I know that n is 35 bigger than or equal to 30. But if you give me 35 points, how do I know that population is normal or not? Like how do I check assumption number 2? That's a very valid question. You don't have to check for your exam problems. I mean, of course, like we statisticians have to check, but for you, for exam, you do not have to check assumption number 2. In the question itself, they will say it's normal. Like, sorry for this small spelling error. The population, okay. So the population is normal or close to normal. So you don't have to check that. The question will give you that. So once everything is okay, That means, like, you know mu, you know sigma, and the assumptions are satisfied. I mean, one of those is good enough. Either one or two is satisfied. Then that's the CLT. This is the CLT. You are done. X bar follows normal with mean mu x bar is mu and sigma x bar is sigma by square root of n. So once again, for x1 through xn, so for example, take x, suppose 5. So what's the mean of x5? The mean is mu. And what's the standard deviation? It's sigma. Similarly for x1, x2, all of them. Now, for x bar, it's a different story. For x bar, what's the mean? Mean remains the same, mu. What's the standard deviation? It's sigma by square root of n. So whenever people talk about mu or sigma, that means, whenever people talk about mean, the mean is this. You have to ask him, mean of what? So mean of x5 is mu. Mean of any xi is mu. But mean of x bar is also mu. Standard deviation of x5 or any xi is sigma. But standard deviation of x bar is sigma by square root of n. So always ask the question, mean of what? Standard deviation of what? So that's it. If conditions are satisfied, by conditions I mean this page. If this page is good, then this happens. That's your CLT. So this is CLT. Done. And obviously we'll apply this in the problems. So that will come in the next video.